Measurement of the diameter of the moon. The situation is shown in the figure. AB represents the diameter of the moon. R is the distance between Earth and the moon, and the angle made by diameter of the moon at any point on the Earth is theta. Here theta angle is subtended by two diametrically opposite ends A and B of the moon at a point E on the Earth. The diameter of the moon are distance of the moon from Earth. Now we have theta equals to arc by radius equals to d by r. So measuring theta d can be calculated if r is known. Now r can be measured with the help of parallax method, which I am going to discuss next. Parallax method. This method is used to measure the distance of planets and stars from Earth. Parallax. If we hold a pen in front of our eyes and then look at the pen by closing the right eye and then left eye, we observe that the position of the pen changes with respect to the background. This relative shift in the position of the pen object with respect to background is called parallax. The distance between the points of observation, in this case the distance between left eye and the right eye, is called the basis. Parallactic angle. The angle theta subtended by the basis at the object O is called parallactic angle. Parallactic angle equals to length of arc divided by radius, or theta equals to b by s, where b is the base and s is the distance from left or right eye to the object O, or s equals to b by theta. In the case of an astronomical object such as nearby a star, the theta angle subtended at the eyes will be extremely small and can not be measured. To overcome this difficulty, two observation points E1 and E2, quite distance apart on Earth, are chosen so that E1 E2 equals to B, as shown in the figure. The angle theta can be determined only if we observe the object O simultaneously from E1 and E2 on the Earth. This is not possible. However, we select a distance star O dash, whose position and direction can be approximately considered the same from E1 and E2. The angle O dash E1 O equals to phi 1 and angle O dash E2 O equals to phi 2 are measured with the help of a telescope. Clearly from the figure, angle E1O E2 equals to phi 1 plus phi 2 equals to theta. Hence distance s equals to b by phi 1 plus phi 2 can be measured. Third, reflection method, echo method. First one, determination of thickness of matter sheet. In this method, we send a signal in the matter which after reflection comes out, and we note the time taken by going to and returning to the point, and then we calculate the thickness of matter sheet. In a public, consider the d is the thickness of the matter and time elapsed from the moment the signal was sent and the time when the reflected signal echo is received. Hence we have t by 2 equals to time taken by the signal to travel a distance d, thickness of the sheet. If v equals to a speed of signal, then d equals to v into t by 2. And from this formula we can calculate the thickness of sheet. Second, measurement of a distance of a hill. Here same method is applied. We send a signal and then receive it. We note the time of we note the time of sending signal and receiving it, and then we calculate the value of d. Here t equals to time to hear the echo, so t by 2 will be the time to reach the hill. Now v equals to a speed of sound, then t equals to v into t by 2, and we know that the velocity of sound is 344 meter per second at 22 degrees Celsius in air. So we can calculate using this method the distance of hill from the formula d equals to v into t by 2. Third is radar, radio detection and ranging. It is a device to detect the aeroplane in the sky and to measure its distance from the radar station. Radar works on the principle of reflection of waves or echo. Here t time to reach the aeroplane and come back to receiver. Hence s equals to dhwani, s equals to c into t by 2. The corresponding figure is shown in corresponding diagram is shown in the figure. A antenna is used to send the signal and same antenna is used to receive the signal, and time is noted between two events, and from it we get the formula, get the distance between aeroplane and radar station. S equals to c into t by 2, where t is the total time taken by signal to go to the aeroplane and come back to the radar. Fourth, sonar, sound navigation and ranging. It also works on the principle of reflection of ultrasonic waves, that is echo. This is used in the sea. Here a ship is shown which is in the ship, and we sense a signal which distance we have to measure, and we note the time taken by signal to go to that point and return again to the ship. Here t equals to time to go and come back to the receiver. V equal to a speed of the signal in water. Hence d equals to v into t by 2. So from this formula we can calculate the distance between object and the ship inside the sea. For example, the shadow of a tower standing on a level plane is found to be 100 meters longer when sun's altitude is 30 degrees than when it is 60 degrees. Find the height of the tower. Here the situation of this problem is shown in the figure. There is two elevations, one at 30 degree and one at the 60 degree. If here h is the height of tower, then as previously we have calculated the formula h equals to d by cot theta 2 minus cot theta 1. Putting the value and solving it, we get h is equal to 50 root 3 meter. Answer. Question. When the planet Jupiter is at a distance of 824.7 into 10 to the power 6 km from the Earth, its angular diameter is measured to be 35.72 seconds of arc. Calculate the diameter of the Jupiter. The systematic diagram is shown in the figure. The distance of the Jupiter from Earth is given as equal to 824.7 into 10 to the power 6 km, and angular diameter theta is given 35.72 second. Now we should convert this second into radian, and we know that the formula for converting second into radian is to multiply 35.72 into 1 by 60 into 60 into pi by 180, and solving this we get diameter of Jupiter d equals to s into theta, and putting all value we get the value of d equals to 1,48,217.8 kilometer. That is, the diameter of Jupiter is 1,48,270.8 kilometer. Example: in a submarine equipped with a sonar, the time delay between generation of probe wave here means signal, and the reception of its echo after reflection from an enemy submarine is found to be 77 seconds. What is the distance of enemy submarine? A speed of sound in water is 450 meters per second. The distance of enemy submarine is given by S equals to V into T by 2. Using all value we get 55,825 meter answer. Now intensity method, inverse square law method. This is a spectroscopic method based on inverse square law. According to this law, the intensity of illumination at a point is inversely proportional to the square of the distance from the source of light. That is, this method is used based on the properties of light. It is assumed that brightness of all stars is same. Their brightness appears to be different because of their relative distance from us. The photograph of a star of known distance r and that of another star whose distance r2 is to be measured are taken. If I1 and I2 be their intensity of illumination, then according to inverse square law, I1 by I2 equals to R2 square by I1 R1 square, or R2 equals to R1 into I1 by I2 to the power 1 by 2. Using this formula, we can calculate the unknown distance of unknown star. This method is employed to estimate roughly the distance of distant stars at 100 light years or so from Earth. Means that if a star is more than 100 light years, then this formula can be applied directly. This will give you a estimated distance of a star. Now, determination of the distance of the inferior planet from the Sun and the Earth. Copernicus method. This method is also known as Copernicus method because this method was developed by Copernicus. He was an astrophysicist, not astronaut. Copernicus was an astrophysicist. The planet like Mercury and Venus, which are closer to the Sun than the Earth, are called inferior planets. The orbit of Earth and planet about the Sun is assumed circular. The angle formed at the Earth between the planet and Sun and between the direction of the planet Earth and the Sun Earth is known as elongation of the planet. This angle is not fixed due to the orbital motion of the planet and so Earth. Consider the state or position of the planet P and the Earth when angle SPE equals to 90 degree. Now sin E equals to RP S by RES. Hence RPS equals to 1 astronomical unit into sine E. Similarly, cos E equals to REP by RES, or REP equals to RES into cos E. Hence REP equals to 1 astronomical unit into cos E. From this formula we can calculate the distance between Earth and planet. Problem. The angle of elongation, the angle of elongation E of the planet Mercury is 24 degree. Find A, the distance of the Mercury from the Sun, and 2, the distance of the Mercury from the planet. Here given value is RPS, that is distance between planet and Sun, equals to 1 AU into sine E, and RMS, that is distance between the Mercury and Sun, 1 AU into sine 24 degree. Solving this we get 6.1 into 10 to the power 10 meter. Now we have REP equals to 1 AU into cos E. Hence REM equals to 1 AU into cos 24 degree. Solving we get 1.37 into 10 to the power 11 meter answer. Suppose the orbit of the Mercury around the Sun is circular and the radius of this orbit is 0.38 astronomical unit. Find 1, the angle of maximum elongation for the Mercury, and 2, the distance of the Mercury from the Earth at this instant. Here RMS, distance between Mercury and Sun, is given 0.38 astronomical unit. Now using formula we had RMS equals to sine E into AU. This implies 0.38 AU equals to sine E into AU. So sine E equals to 0.38, or E equals to sine inverse 0.38 equals to 22 degree 20 minute, 22 degree and 20 minute. Second, RME 1 AU into cos E, 1 AU into cos 20 degree 20 minute, 22 degree 20 minute. Solving we get 1.388 into 10 to the power 11 meter. Determination of the distance of the superior planets. Previously we have seen the determining the distances of inferior planet. Now we are going to discuss about the distances of the superior planet. The planet like the Mars, the Jupiter and Saturn, which are farther from the Sun than the Earth, are known as superior planets. The planet which is more away from the Earth is called superior planet. Copernicus used Kepler's third law of planetary motion to determine the distances of the superior planet from the Sun. According to Kepler's third law of motion, the square of the time period of revolution of a planet around the Sun is directly proportional to the cube of the semi-major axis of the orbit. That is T time period, a square of time period proportional to cube of semi-major axis, that is T square proportional to R cube, where R is the semi-major axis. Here we are considering the orbit is elliptical, not circular. The situation is shown in the figure. A planet is shown and a Sun is also shown, and a elliptical orbit is shown. Elliptical orbit of a planet around the Sun. Let T1 and T2 be the time period of two planets, and R1 and R2 be the semi-major axis of the orbit of these two planets respectively. Then T1 square proportional to R1 cube and T2 square proportional to R2 cube. Hence T1 square by T2 square equals to R1 cube by R2 cube, or R1 by R2 equals to under root T1 by under bracket T1 by T2 to the power 2 by 3. And using this formula we can calculate the distance of superior planets. Now reflection method, laser method. The word laser stands for light amplification by stimulated emission of radiation. The laser light can travel long distances without fading its intensity. A laser beam is sent toward the object, for example moon etc., whose distance is to be measured and its reflected pulse is received. If t is the time elapsed between the instant the laser beam is sent and the return back, then the distance of the moon from the earth is given by s equals to c into t by 2, where c is the speed of light, which is equal to 3 into 10 to the power 8 meter per second, where c is used because laser is also a light. Laser is also a light. Laser beam is also a light. So velocity will be equal to the velocity of light. Indirect method for the measurement of very small distances. Length up to 1 millimeter can be accurately measured by meter scale. To measure distances up to 1 by 10 millimeter, a vernier calipers is used. A screw gauge and a micrometer are used to measure distances up to 1 by 100 millimeter accurately. To measure distances of the order of 10 to the power minus 7 meters, sensitive optical microscopes are used. Distances of the order of 10 to the power 9 meter are measured with the help of electron microscope and tunneling microscope. However, to measure still smaller distances, such as the size of an atom or a molecule of a liquid, we use following indirect techniques. Now, atomic radius by Avogadro's hypothesis. When large number of atoms are packed together, some empty spaces are left between them. According to Avogadro's hypothesis, the actual volume occupied by the atom is 2/3 of the volume of the substances. If m be the molecular mass of a substance, the number of atoms if m be the molecular mass of the substance, then the number of atoms in it is an Avogadro's number. Consider m gram of the substance. The number of moles in the substance m by cap m, and the number of atoms in it m by m into n. If r is the radius of each atom, then volume of atoms in substance v atoms equals to m into cap n by cap m into 4 by 3 pi r cube. Now, if rho is the density of the substance, then its volume v substance equals to m by rho. According to Avogadro's hypothesis, v atoms equals to 2 by 3 v substance. So, m into n by m into 4 by 3 pi r cube equals to 2 by 3 m by rho. From this we get value of r equals to under bracket cap m by 2 pi n rho to the power 1 by 3. Based on above theory, let's solve a question. For example, 1 mole of an ideal gas at STP occupies 22.4 liter. What is the ratio of molar volume to the atomic volume of a mole of a hydrogen? Why is this ratio so large? Take the radius of hydrogen molecule to be 1 angstrom. Here radius of hydrogen molecule is given R equals to 1 angstrom equals to 10 to the power minus 10 meter. Now atomic volume of 1 mole of hydrogen. Avogadro number into 4 by 3 pi r cube. Here R is the radius of the hydrogen atom. Or equals to 6.023 into 10 to the power 23 into 4 by 3 pi into 10 to the power minus 10 to the whole cube. We get 25.2 into 10 to the power minus 7 meter cube. Atomic volume. Now molar volume equals to 22. That is 1 mole of hydrogen. Volume of 1 mole of hydrogen is called molar volume of hydrogen. The 22.4 liter, which can be converted into meter. 22.4 into 10 to the power minus 3 meter cube. Hence molar volume by atomic volume 22.4 into 10 to the power minus 3 divided by 25.2 into 10 to the power minus 7, which comes out to be 0.89 into 10 to the power 4, equivalent to 10 to the power 4 in terms of order of magnitude. This ratio is so large because the actual size of the gas molecules is negligible, small in comparison to the intermolecular separation.